And I did shift over here, didn't I? Yeah. Okay, so the moment equations. That's the rolling moment equation. And then we're also going to do the pitching moment equation. Leave some space here so that we can substitute and fill in. So here's the pitching moment equation. Oh. Jump down to the next step. So those are the equations that we got. Those are nonlinear because you get stuff like Q times R, P squared, R squared. So those are the nonlinearities that keep us from Laplaceing it. Make sure I grabbed everything. Yeah, and so then we need the steady state or equilibrium equations. And so we refer back to that steady state flight condition where we were only flying forward. We had a forward speed and that was it. And we had no P, Q, or R. That is no pitch rate, no roll rate, pitch rate, or yaw rate, because we were saying we're flying straight and level. It's a cruise flight condition. If we were doing say a pull-up, then we would have a Q0 term in that, because that steady state pull-up would have a pitch rate, a constant pitch rate. But we're not doing that. For this, we're just doing the cruise flight condition. So if all of the rates are 0, you can see that these equations become pretty simple. All right, there's no P in the steady state condition. There's no R, there's no Q or R. So all of this stuff boils down to this. And then the same thing for the pitch rate. The steady state flight condition is like that. And you look at that and you go, okay, the sum of the moments is 0, that's pitch trim, right? So that makes sense. This is a steady state trim condition. This is pitch trim, this is roll trim. So that makes total sense. All right, so then we do step 1 is substitute. So we go back to that list of all of the steady state variables plus the small perturbation variables. And we're substituting up here, so we get an L0 plus delta L. And again, if I were doing this, I would put a delta here. But that's just the perturbation is P. There is no P0, so we don't have a P0 dot here because we've said P0 is 0. So the substitution here was pretty easy because there weren't very many. Like in the steady state, all we really have is a U0. All right, so I'll probably end up with 2 files, but I'll figure out how to merge them together. Thanks for the heads up. All right, so we substituted here. So that's step one. And step two would be to say that P0 dot is 0, but we don't really need to do that because P0 is 0 anyway. Step three is to neglect small products. So we look at every time there's a small perturbation multiplied by another small perturbation, and we knock that out. So we look at this, and we say this is a small product. And same thing here, we got P times Q, they're both small. So what we're really saying is this is smaller than some of the other terms that don't have products. And we don't have to deal with the sines and cosines here, so actually the moment equations are way easier because that's all you're doing. So that's step three, and then step four is to subtract the steady state equation. And this is super easy because the steady state equations are just this. So that means the only steady state part you see is the L0. So then you get that's gone, that's gone. So I think that's it. Let me draw a line here because I kind of crammed the stuff together. So this is our small perturbation rolling moment equation. And what's left to do with this then is to put in the small perturbation rolling moments there. I'm going to do this one for you, and then in the homework you're going to do N. Same process. We substitute, so step one. There is no Q0, so we don't have a Q0 dot. There's no R0 or P0. So it really looks like we're just copying the equation down again, but we're not. And that's why if it were me, I would put those deltas on there. So now we would end up with a delta R, a delta P squared, and a delta R, because then it makes it real obvious. So that's step one. There is no step two. So we don't really do that, although I'll list it here just because it's step two. Step three is to neglect these small products. So that's step three. And this step would be more involved if we had, say, a Q0 or a P0, because then you'd have a P0 plus P squared here, and you'd have more terms. But with the cruise fly condition, it's easy. So that's step three, and then step four is to subtract the steady state. And all that is M0 is 0. So we get our final equation, which I'm going to write down here so I don't have to kneel down. So that's a short equation because the other stuff goes away. So we're good there. Typically, we want to put these in state space form, which is our next step. In the book, at this point, he solves for Q dot to get it all by itself. And then the two equations here, both there's P dot and R dot in two different equations. And so he solves those to get the final set of equations. In other words, he wants to get each equation, just like in state space form, you want single dots on the left and nothing else on the right. Yeah, you have a question? Oh, I'm not, for the guys on Zoom, I'm not saying that we should do that. It was, if I were writing this textbook, I would put deltas in here and make it obvious. Like, remember when we were defining these steady state terms, he did this, and I said, well, I would prefer to have a delta there just to make it obvious. So that's what I was saying. But we're not doing that. We're sticking with the book, because if we try to do two different formats, then we'll just get confused. Yeah, because you look at this and you go, well, we just copied it down, but you didn't. You substituted in, but we used the same variable p for p, total p, and that's why I think it's confusing with what he does. What it does is it makes it easier to write, correct? Because we don't have to put all the deltas in every time we write these. So you just have to mentally say, okay, in the small perturbation equations, these are the small perturbation. In the nonlinear equations, those are the full deal. So if we take the three force equations, and we put all of the dots on the left side, and if we take the three moment equations and we put P dot, Q dot, and R dot on the left side, it's just rearranging. You just shove stuff on the right, and then like here we divide by IY to get Q dot all by itself. Here we got a P dot and an R dot in both the rolling moment and the yawing moment equation, so you have to solve two equations simultaneously to get P dot and R dot. But that's just algebra. And so what you end up with is and he does that mainly just to emphasize that this is the U dot equation, this is the V dot equation, this is the W dot equation. Again, there's still more to do. We need to figure out what essentially the drag, side force, and lift force are. And then if you do the P dot, Q dot, and R dot equation, again, we have to do that solving, so that's why you get this weird term here. And so we have a P dot equation, a Q dot equation, and an R dot equation. And you look at this and you could say, yeah, they're linear, so we can Laplace these. All of this stuff is in your book. It's on these equations are on page 109 in your textbook. Because hopefully I've copied them up here correctly. Hopefully you get them copied in your notes correctly, but they're in the book. So the process that you need for your homework is to do exactly this on those two, the z-force equation and the yaw moment equation. So show me all 4 steps, and that's what I'll look for in the homework. So again, the reason for this is that the equations are nonlinear, so we either integrate them on a computer or we want to be able to do some analysis on them. And so we're resorting to doing this because we can Laplace, and then we can talk about the roots of these different equations and talk about the motion that we get for the airplane, just like we did for the mass spring damper system. Does it oscillate? Does it not oscillate? Does it just slide over and stop? We want to know that for the airplane. All right, so I'm going to walk through doing this equation here and figuring out what delta z is. We're not going to go through all the details of all the equations, and I won't ask you to do that for homework. But I do want to show you how one of them works so that you understand where the terms come from. We're in detail up to here. But then we're going to separate the equations out into longitudinal and lateral directional and talk through what you get if you do this analysis. And the details of the algebra, I'm only going to show you for this one, and you're just going to have to trust that the book has the right equations for the rest of them. Makes sense? So now what we're having to do is put the aerodynamics the forces and moments into the equations. And we can separate these out into longitudinal and lateral directional because the equations don't couple together between them. And we saw that when we were doing trim, right? We could solve the lift and the drag and the pitching moment equation separate from the roll, yaw, and side force. And aerodynamically, the airplane's decoupled that way as well. I lost an L. Thanks again for the reminder. I appreciate it. Yeah, it's Monday, so it's one of those Mondays. So we're going to do just the W equation. And in fact, what we're going to talk about is what is delta Z. Now I'm pointing to that and I switched. So let me switch back real quick. So we're talking about the delta Z. So I'm going to show you where we get that. So we're working on the W dot equation and we're going to try to find out, well, what is delta Z? Well, if you remember, delta Z came from, it's the small perturbation part of the total force Z. And because we chose stability axis, Z is perpendicular to V infinity. And so that means that Z is in the minus lift direction, right? Z is down, lift is up, lift is perpendicular to V infinity up, Z is perpendicular down, and so that makes things really easy here. That's one of the reasons that people use stability axis. Otherwise, you end up in the equations of motion with both components. You got the lift and the drag, and so the expression becomes twice as big. So that's the major reason people use stability axis in the dynamic analysis. All right, so we do just our normal build-up. What we need to do is calculate CL, because CL times Q infinity S is going to give us the lift, and that's going to be the negative Z. And so those are the variables that we say the lift depends on. And they're the normal ones, right? We have some zero lift, or we have some lift at 0 alpha. And then this is our lift curve slope times alpha. This is for the whole airplane. And then the elevator changes the lift, right? And then when we talked about a pull-up, the airplane's pitching. And so we have to get some lift due to the pitch rate because the tail is sweeping down. And we added that in the pull-up, but this is new. This is an alpha dot effect, and it's based on the lag in the downwash from the wing to the tail. And that's really all I want to say about it, is the wingtip vortices come from the wing, obviously, and it takes them a little bit of time to get to the tail. And so if you change an angle of attack at the wing, it takes a certain amount of time for that change in angle of attack to get to the tail. And its model is an alpha dot effect, because the faster you change angle of attack, the more that lag is apparent in the aerodynamics of the tail. Well, we could go through a half an hour lecture on how that's done, and I'll do that in 714 if you guys ever take that. But for now, it's just the lag in the downwash, and so we throw in an extra term here that allows us to include that. All right, so the way we build this up, and again, we're just going to do longitudinal, so I'm going to erase the lateral directional. We're going to say the Z force is minus CL times Q infinity S. That's nothing new. And here's where we're going to write alpha as the steady state alpha plus the perturbation. So this is our trim alpha. We trimmed the airplane. We've done that since a long time ago. And then here's our trim delta E. And notice instead of putting the word trim there, it's because I'm shortening it, that we just put a 0 in it because we're talking about now the 0 as the steady state. And so the steady state is our trim condition, but instead of writing trim there, we're just going to write 0. I'm over on this board, right? Yeah, good. And we don't have to differentiate that with the Q term because remember, with the trim condition, there is no Q. So this is just the perturbation. And the same thing with the alpha dot term. There is no change in the angle of attack in the trim condition, so there is no alpha dot 0. And so this is where the steady state stuff comes from. And then here's where the small perturbation stuff comes from. So we write this, we collect all of the steady state stuff as a Z0. So that would be this term here, and this term, and that term. And then we collect everything else into terms that they call ZW, ZQ, delta ZC, and ZW. And that is just the terms that when you multiply everything together, there's where W is, right? Alpha is W over the forward speed. So we substitute everything in, and then we just collect it all into this ZW thing. And then ZQ is just everything that multiplies by Q, and ZW dot is everything that multiplies alpha dot. And again, I'm not going through this step. There's just a lot of algebra here because we have to substitute in what Q hat is. Remember what Q hat is? It's Q C bar over 2U1. And this is alpha dot C bar over 2U1. That's how it's defined. And we have to substitute in for delta alpha. So hopefully in your mind, you're saying, thank you, Dr. Steck, for not going through all of that algebra. Again, we can't do all of the algebra for all the equations, but I want to walk you through where this different stuff comes from and tell you that all the formulas for this stuff is in page 118. So what it means is you go to page 118, you look up ZQ, and then you stuff in the numbers for it, and you get a number that goes there times that variable. And just as an example, let me write one of those up here. Are you guys caught up here? Then I can switch to the other. And so what we did was we just derived delta Z. It's the part that's left over that's not Z0. Everything else is delta Z. And so like that ZW, this is on page yeah, we're good. So there's the formulas there. And so our W dot equation then plugging in for delta Z is all that stuff plugged in here, and we get a W dot equation. So I'm substituting in for that. Leave a space here because I'm going to add something in. I'll get it right. This is ZW times W plus dq times q plus z w dot times w dot. So that's delta z. Here's the control term that has the elevator in it. So in reality, all I did was multiply by m again to get the m out from under the delta z. This is our delta z that we derived on the other screen, the other board. This is our delta z. The w term, this is the alpha term, the q, the w dot, and wz. And if you look in your book, he adds in another effect that's the u effect, the forward speed effect. So it turns out that forward speed perturbations can be important when you're flying close to Mach 1. Because when you're really close to Mach 1, a small change in airspeed changes the shockwave pattern on the wing and the fuselage. So this is really a Mach number effect. And as it is with almost all of these effects, how were they discovered? Because you look at that and you go, well, why would I put that in there? People, when they were flying low speed, they didn't need that term in there, and the other equations worked fine. They knew angle of attack, pitch rate, and those all make sense. But when they started flying close to the speed of sound, they started comparing wind tunnel tests and flight tests to the models, and they didn't match, and so they started looking for a problem. And they found out, well, there's an extra effect here. And in fact, that's how almost all scientific discoveries are made, is that they start taking observations, and then they look at their model and they see that there's a difference between the model and what they're predicting, and they look for reasons. And that goes all the way back to like Galileo observing the planets going around the sun, right? You guys talked about that in physics, that there were all these weird theories to explain how the planets move through the sky because they didn't follow perfect circles. And the thought back then was that everything revolved around the Earth, and so they should see the planets going around the Earth, but they didn't. And so they came up with all these weird theories called epicycles. Have you heard of those? I mean, there's a mathematical formula that described how that planet went around the Earth, but did these weird loops because it was actually going around the sun. And so was the Earth. So the Earth's going around the sun. These are, so we know that now. It's like common knowledge. But they came up with complex math models to explain how the planets moved in these weird motions. And then somebody said, hey, wait a minute, maybe everything's going around the sun. And it all became really simple again. So that's how these things are discovered. This happens all the time. It's how the relativity was discovered, because they found out that the speed of light was constant no matter which direction it was traveling, and everybody scrambled around to figure out how to explain it. So even in aerodynamics, all of these effects happened when we expanded the envelope of how we flew the airplanes. How are we doing on time? 10 minutes. So this equation is for W dot. And so we stick it in state space form. That's easy. Actually, we got a little bit of a problem, right? Because we got a W dot over here and a W dot there. So how do we fix that? We put both W dots over here and then divide by M minus ZW dot. So we rewrite this. And that's why I had you guys go through that exercise with the simple equations, so that you go, okay, it's the same thing. We're just going to move the W dots over here and then divide by this to get the state space form. So I move that over, and then we divide, so you get W dot. And then you get these weird combinations, but that's just part of the algebra. And there's our state space form. If we do this carefully and we put everything in order, then here's our variable and here's the thing that goes in the matrix. Here's our variable, here's the thing that goes in the matrix. I lost my Q, there's my variable. There's the thing that goes in the matrix. And then this is the right-hand side forcing function. That's that column vector that we do. So we've just done one of 3 longitudinal equations, but it's the exact same process for all of the other equations. And so the full matrix form, I'll just write this one in over here, and then I'll refer to you in the textbook where they did the other equations that go in there. So here's what the matrix looks like. And again, I'm only going to fill in that one equation, and the book will fill in the rest. Leave a space down here because I'm going to fill in another equation. Leave a space here. And then we're filling in the W dot equation here. So if we did the other board correctly and we did them in order, then all we do is just copy stuff across. And then there's terms up here. And here's the Q dot equation. So this comes from the pitching moment equation. This comes from the drag equation. This is the lift equation. And so what's missing out of this? In this term here, there's a whole column here. In this term here, that gets multiplied by delta theta. So we have to include that. Go back to the equation here. Let me shift back over to the other screen. We have a delta theta in this equation. So I had to include that in the vector, right? Because it's there. It's a small perturbation variable. But what's delta theta dot? Because I'm missing an equation for delta theta dot. Yeah, so now we have to think, well, what is theta? Theta is the pitch angle, right? Yeah, so delta theta dot is related to the pitch acceleration, right? Or actually the pitch rate. So there's an equation from the kinematic equations that says that Q is delta theta dot. And it makes total sense because theta is the pitch angle. And so what's the derivative of pitch angle? It's pitch rate, which is what we call Q. And that's already in our equations. And so that's easy to fill in, is that delta theta is equal delta theta dot is q. And that's exactly like what we did where we said, well, we call x dot the velocity in the x direction. Here we're saying theta dot is the pitch rate. We just call it that. And the rest of this is on page 112. And so that's what's on page 112 and we just did that the second row across is what we did. And so now we're going to Laplace that. And at this point, you're thinking, what a giant mess, right? A lot of equations, a lot of terms to keep track of and all that stuff. But inside all those terms in there are just the wing area, the horizontal tail area, all of the geometry of the parameters of the airplane and the lift curve slopes of all that stuff. So it's really just stuff we already know how to estimate. And you just crunch the numbers, and then inside the matrix, you just get a number everywhere you see all that stuff. So you calculate it. And it is complicated. I mean, the trim solution was complicated enough. And the fundamentals are that you definitely want to make sure you can trim the airplane before you get off the ground, right? Otherwise, you're going to die for sure. You want to be able to trim at all airspeed. So we start with that. That's fundamental. You want to be able to do the equilibrium condition at all flight conditions. But now we want to know, well, how does the airplane behave when the pilot perturbs something? Or we hit a gust and we get an alpha perturbation. And that's important as well. And so you have to go through these calculations to figure out how your airplane flies dynamically before you build your prototype. Because this is a lot cheaper, even though it's a giant mess. You can do it and you can do the calculations in a week. Whereas building a prototype, you guys are building airplanes, right? And no, you guys aren't in senior design. I'm thinking on the other class. In senior design, you'll get to the point where you've designed your airplane on paper, and then you go to build a prototype, and it takes a lot of time to cut the wing out and put it all together. And you want to make sure before you take off that you at least have some hope of staying in the air, and that your pilot will be able to handle the dynamics of how the airplane behaves when he's trying to come back in and land your airplane. So it's worth doing the calculations, even though it's a mess. And in the real world, when you're building big airplanes, it's really expensive to build a prototype. So it's worth doing all this analysis. Even if you guys are structures guys, which I know a lot of people are, in the structures end, you spend a lot of time doing simulations of structures and calculating structural analysis for the same reason. You want to make sure your wing doesn't break off when you take off or do a pull up. So next time we'll talk about, well, what do you get when you Laplace this? I'll talk you through it, but what we really want to talk about is, well, what are the common modes of motion? Remember the mass spring damper system with the two masses? We got two different ways it could move around, two modes of motion. Well, it turns out this has three modes of motion, and they determine how well the airplane flies. So I want you to at least become acquainted with what the names are and how we look at the eigenvalues of this matrix to figure out, well, what do we get as far as the motion of the airplane? Because when you go into industry, whether you're doing structures or aerodynamics or whatever, at some point, people will be talking about these modes of motion, and I want you to know what they are and what they're talking about. Okay, that's it for today. You got homework on Wednesday, which is not up to this point. We covered the small perturbation. That's what you guys are doing in there. So go through that and show me the steps.